Hi everyone. Today we are going to discuss about crystal field theory splitting of d orbitals. Before going to crystal field theory splitting, first let us discuss about 5 degenerated d orbitals orientation. So generally these 5 d orbitals present in the two different orientations. The dx square y square and z square is having one type of orientation. Remaining 3 is having another type of orientation. That means when you see the x square, y square, the lobes are present on the axis. Means, for example, let us take this is the x axis, this is the y axis. Exactly the lobes are present on the axis. Similarly, z square, this is the z axis. One lobe is present on the axis, that is the z, and another one is present around the z axis. Like that, x square, y square and z square orbitals present on the axis. And when you come to xy, xz, yz orbitals, these lobes are present between the axis. For example, let us take dxy. So this is the x-axis, this is the y-axis, and exactly the lobes are present between the x and y. Similarly, xz. So this is the x-axis, this is the z-axis. Exactly the lobe is present between the x and z. And when you come to yz, this is the z-axis, this is the y-axis. Exactly the lobes are present between y and z. Like that. So yz, xz, xy orbital lobes are present between the axis. X square, y square, z square orbitals present on the axis. This you have to remember to understand the crystal field splitting. That means orientation of the orbitals. First two orbitals are present on the axis and the next three orbitals present between the axis. Next let us come to why the splitting of orbitals takes place in the complex compounds. Generally, when a ligand approaches to the central metal ion, the negative charge or lone pair of electrons present on the ligand will interact with the metal's d orbitals. That means when this ligand negative charge or lone pair is interact with d orbital, it causing the splitting of energy levels. Why the splitting of energy levels takes place? Ligand is having negative, that is the negative charge or lone pair, and orbital is also a negative. The repulsion takes place between negative and negative, that is negative of the ligand and negative of the orbital. That's why they are causing the some repulsion, it is causing to splitting into the energy levels. And when you come to this splitting, again it is depends upon the so many factors like nature of the metal atom or metal ion, nature of the ligand, oxidation state of the metal or metal ion, coordination number of the metal or metal ion, and arrangement of the ligands. These are the some of the factors affecting the splitting of d orbitals. That means when metal ion changes, automatically energy changes. When the ligand changes, same thing, energy changes. When the oxidation state changes, or coordination number changes, or ligand changes, that is the arrangement of the ligand changes, automatically the energy will also changes. Let us discuss about the splitting of the different geometries. First let us discuss about splitting of d orbitals in octahedral field. To understand the splitting of d orbitals in octahedral field, first you have to know about the what is the octahedral structure. Generally, in the octahedral structure, total 6 ligands are present on the central metal ion. And in these 6 ligands, 2 ligands are present on x-axis, 2 ligands are present on y-axis, and 2 ligands are present on z-axis. That means total 6 ligands, 2 are on x, 2 are on y, and 2 are on z-axis. And when you see the octahedral structure, generally it will be look like 4 ligands are present on the plane, 1 ligand is above and 1 ligand is below. And the bond angle among all the orbitals is equal to 90 degrees only. That means in case of the octahedral structure, all the ligands are present on the axis. That you have to remember to understand the octahedral splitting. That means total 6 ligands, 2 are on the x-axis, 2 are on the y-axis and 2 are on the z-axis. Now come to how these orbitals are splitting in the octahedral. And when you come to this diagram, this is the isolated atom degenerated orbitals. That means when the central metal ion or metal is isolated, means when it is not bonded with the ligands, all the orbitals present on the central metal ion are degenerated, means all are having the same energy. But when the ligands are come close to the central metal ion, all the orbitals energy will start increase. That means when they are coming from far away, that is the ligands are coming from far away to the central metal ion, the energy of all the orbitals will be increased and reaching a point. And after that, when the ligands are close to the central metal ion, then the splitting of the orbitals will take place. So that means when the ligand is having more repulsion toward the orbital, will get the more energy, and when the ligand is having less repulsion toward the orbital, will get the less energy. And in case of the octahedral splitting, already know that one, x square y square orbitals present on the x and y plane, and z square orbitals present on the z plane. And in case of the octahedral geometry, ligands are present on the axis. See here, 2 ligands on x, 2 ligands on y and 2 ligands on z. That's why these orbitals x square, y square and z square orbitals are very close to the ligand. Due to that reason, the more repulsion takes place. When they are getting the more repulsion, the energy will increases. So see here, the dx square, y square, z square orbitals which lie along the axis, means they are present along the axis, experience greater repulsion and have the higher energy. So due to the reason, these two orbitals will split into higher energy. And similarly, when you come to remaining three, xy, yz, zx, these orbital lobes present between the axes. For example, dxy, one orbital. So let us take this is the x-axis, this is the y-axis, and this is the z-axis. Exactly, the lobes of the orbital present between the, what is that one, x and y. This lobe is here, this lobe is here, this lobe is here, this lobe is here. That means in case of the xy orbital, the lobes are present between x and y. Similarly, yz. So let us take that this is the z orbital and this is the y orbital. Here the lobes are present between the y and z. Let us take the xz. This is the x orbital, this is the z orbital. Exactly these lobes present between the, that means in case of the these three orbitals, are lobes are present between the axis and ligands are present on the axis. Generally the ligands are here. When you come to ligands, they are present on the axis, the lobe is present between the ligands. That's why these will get the less repulsion compared to these two. That's why, see here, the dxy, yz, xz orbitals which lie between the axis experience less repulsion and have lower energy. So due to the less repulsion, they are moving into the lower energy. Like that, in case of the octahedral splitting, these two orbitals will get the more repulsion. Due to that reason, they are moving into the higher energy, and these three orbitals are getting less repulsion and they are moving into the lower energy. That means when the total 6 ligands are attached to the central metal ion, the total 5 degenerated orbitals will split into two energy level. One energy level is called Eg, another energy level is called T2G. Eg is the higher energy level, present 2 orbitals, and T2 is the lower energy level, contains 3 orbitals. And the energy difference between these two energy levels is equal to delta O. O is nothing but that is octahedral. The energy difference will be known as that is delta O. And in this case, generally the Eg level orbitals getting the more energy, that is almost equal to plus 3/5 delta O, and T2G level orbitals are losing the energy, that is almost equal to minus 2/5 delta O. So that means these are having more energy, that is equal to 3/5 delta O. These are having less energy, that is equal to 2/5 delta O. The difference between these energy is delta O. It is called CFSE, crystal field stabilization energy. Okay, later we'll discuss about this crystal field stabilization energy, how the complex compounds are getting stability due to the filling of the electrons into these energy levels. So this is the splitting of orbitals in octahedral shape. Okay, let us come to next one, splitting of d orbitals in square planar. Same thing, before going to the splitting, first let us come to the what is the square planar shape. So when you are removing the two orbitals, that is the two ligands at yz axis, you can know the octahedral shape. This is the octahedral shape. When you are removing this ligand and this ligand, that is the ligands present on the z axis, and we are getting the square planar structure. If you remove these two, that is equal to square planar. That means it contains the only four ligands, two ligands on x-axis and two ligands on y-axis. It is known as square planar. Total four ligands are present on the plane only in square. So that's why it is called square planar. And when you come to the square planar splitting, it is easy to understand by using the octahedral splitting. Already know the octahedral splitting, e.g. dx square y square dz square t2g dxy dyz and dxz. And when you come to the square planar splitting, there is no ligands on the z axis. That means there is no ligands on the z axis. That's why when you come to dz square orbital, so when come to this dz square orbital, there is no ligands. That's why it will give the less repulsion, because there is no ligand. So when it is having the less repulsion, the energy of this orbital will move to lower energy compared to the octahedral. In the case of the square planar, the dz square orbital will move to the lower energy. And similarly, when you come to these three orbitals, xy, when you come to this xy orbital between the ligand. So in case of the square planar, the ligands are present on x-axis and y-axis. Exactly the xy orbitals present between the axis. That's why it will move to little bit higher energy than remaining two. Because when you come to remaining two, so this is the x-axis, this is the z-axis. Generally, in this case, the lobe is present between the x and z. The ligand is present x and y. The lobe is present between x and z. Here the lobe is present between the y and z. So that means these two orbitals are little bit far away to the ligand compared to xy. That's why the xy orbital is gaining little more energy, and yz, xz orbitals are moving into the little bit less energy. Like that, same thing. So there is no change in the energy of the dx square y square. It will be present at the same place. And dz square is moving into the lower energy. xy is moving into the little bit higher energy. And these two orbitals also moving into the little bit lower energy compared to the octahedral. So this is the square planar splitting. In case of the square planar, we are getting total what is that one? 4 different energy levels. First higher energy is the dx square y square. Next is the dxy. This energy is equal to the what is that one? Delta naught value. And next energy level is the dz square, and the least energy level is the dyz and dxz. So this is about the splitting of orbitals in square planar geometry. Let us come to tetrahedral splitting. So tetrahedral splitting is different compared to the previous two. So to understand this one, first let us come to what is the structure of the tetrahedral. Generally, in this case, the ligands are present between the axes. In the previous cases, ligands are present on the axis, but in case of the tetrahedral splitting, so in the tetrahedral structure, the ligands are present between the axis. For example, let us take this is the y-axis, this is the x-axis, and let us take this is the z-axis. So where the ligands are located? Exactly, they are present between the axis. They are not present on the axis. This you have to remember to understand the tetrahedral splitting. So that means the ligands are between the axis. These are not present on the axis. And let us come to splitting of the orbitals. And in case of the tetrahedral, the energy level is moving into the two energy levels. Higher energy level is having dxy, dxz, yz, and lower energy is having dx square, y square and z square. It is exactly opposite to the octahedral. So why we are getting like that? So when you come to dxy, dyz and xz, these orbitals are little bit near to the ligand. The ligands are at corner. The orbital lobe is between the center of corner. That's why the distance between ligand and this orbital is little bit less compared to the this case. That's why they are having the higher energy. When you come to dx square, y square and z square, the lobe of the orbital is present at the center of the plane and it is little bit far away. In this case the lobe is here and in this case the lobe is here. It is little bit far away compared to this case, that is the xy, yz, xz. So in this case the lobes are present at the center of the corner and in this case the lobes are present at the center of the plane. So that's why these are having the more repulsion is getting more energy and these are having the less repulsion is getting less energy. That means in this case we are getting the total two energy levels. The higher energy level is called T2 energy level, is contain three orbitals, so that is the dxy, dxz, dyz orbitals. And lower energy level is called E energy level. It contains dx square, y square and dz square. So this is the crystal field splitting in case of the tetrahedral. And when you compare the all three splittings, so this is the comparison of the all three splittings. Let us come to first to octahedral splitting. So in case of the octahedral splitting, higher energy is the Eg and lower energy is the T2G. The Eg contain the dx square, y square and z square and lower energy contain the dxy, dyz and dxz. And when you come to the tetrahedral, exactly it is in reverse. The x square, y square will goes to the lower energy and these three orbitals will goes to the higher energy, but energy gap between these two is different. The delta O is more and what is that one? Delta tetrahedral is less. Almost the delta tetrahedral is equal to 4/9 delta octahedral. And when you come to square planar, it is having the total 4 energy levels. The first two energy levels is equal to the what is that one? Octahedral splitting. That means there is no change in the energy of the x square, y square in octahedral and square planar. But what happens here? The z square orbital energy is decreasing and what is that one? Yz and xz orbitals energy is decreasing. There is no change in the xy and x square, y square energy. That's why the energy gap between these two is equal to delta octahedral only. But these two are decreasing. Due to that reason, you are getting the total 4 energy levels in the square planar splitting. So this is about the crystal field splitting of three different geometries, that is the tetrahedral, octahedral and square planar.